Within this video, I share some instructional recommendations to help students succeed in Chapter 1. Here are the different sections within Chapter 1. I tried to list each of these where the learning objectives are in terms a student would understand. So oftentimes the learning objectives are technically correct, but they seem like they're written from one instructor to another instructor. So I try to take the language here and make it a little bit more direct and to help the students understand what they'll be expected to do on exams. The framework for the course begins with aspects of describing matter, looking briefly at energy and properties of matter, and then making and reporting measurements. So this is a guide that I have taking the information in the chapter and showing how the different parts are connected and what the progression is. Looking at this content and thinking about it on our exams, the different sections of learning objectives I show here, and I've stacked these up intentionally in this sort of a pyramid-shaped structure. The ones at the bottom are ones that are typically higher scoring by students on the test, and then they become more difficult as we move upward. So this is good insight to be aware of and to share with students as far as the relative difficulty of different ideas and skills. This thicker line is something that is an important idea or skill that is going to be appearing again and again throughout the semester. The ones that are thicker are high priorities for us. We want to be able to develop those skills because they're going to be essential ones that the students will need going forward. The one I list there in red, that appears on the first test, and it's quite important within lab. Significant figures and calculations is something that students often struggle with or lose points with in lab itself. If I'm looking at these and thinking about common difficulties students have, they're the ones here near the top of the pyramid. Significant figure calculations involving addition and subtraction. That's an area students struggle, and also using conversions with cubic units. Essential for the course, what we want to have them begin to develop and use going forward would be skills involving dimensional analysis and unit conversions. As I just mentioned, significant figures, especially for lab, and being able to understand particle level representations. As a teacher, when I'm thinking about a learning progression and giving feedback, I want to be able to move them towards significant figure calculations that involve mixed operations. They're going to be pretty proficient at applying the rules of addition and multiplication and division. So we want to be able to add to it the rules for addition and subtraction. And also move toward dimensional analysis where we have multiple factors. As we go through a few of these topics, I want to talk about a few different features from sort of a chemical education perspective. These are the chemical triplet, how I think about dimensional analysis and problem solving, and then finally the idea of heuristics as they pertain to significant figure calculations. First of all, the chemical triplet. So this is an idea that's become pretty popular over the last few decades in chemical education, which is, as chemists, we understand chemical phenomena in three different domains. We understand it macroscopically in terms of the observations, the data that we have that we can measure. We think about representing that in terms of symbols, and we can also consider what's taking place at the particle level, at the submicroscopic description. Here would be an example of how the chemical triplet is finding its way into our chemistry textbook. In terms of classifying matter and applying terms like mixture, molecule, compound in different ways. When I say in different ways, I'm thinking about perhaps at the symbolic level, perhaps at the particle level. This is a matching question involving a submicroscopic representation. Here would be one, select the pure substances, where different macroscopic either images or word descriptions are given. In this case, looking at properties of matter, notice within this one we have a particle level representation for solid, liquid, or gas, and below that this is the symbolic representation. This one from the textbook, this is becoming quite common. Notice how all of the different aspects of the triplet are shown. There's the particle level description, There's the formula that's giving a symbolic representation, and in the center here would be a macroscopic representation. As we think about the chemical triplet, the teaching implications, first of all, recognize that you are an expert. You are very fluent at discussing chemical phenomena using any of these, whether it's macroscopic, symbolic, or particle level. And you can easily transfer or change information from one to another. You're far more advanced than a novice would be. A good question for a student would be, well, what's taking place at the particle level? Tell me what's taking place in the beaker. Ask about the submicroscopic representation. Students often rush to use the symbolic information, grabbing the numbers, grabbing the formula, without pausing to think about the particle level description. A great instructional goal would be to try to help the students connect the particle level with the symbolic. Moving on to dimensional analysis and problem solving. In Chapter 1, we introduce briefly the metric system. Initial prefixes that will be useful are millicenti and kilo, as we talk about centimeters, kilograms, milliliters. We add a few more as the course progresses, but those would be good ones to start with. The conversion between cubic units and volume, the bridge between those of a cubic centimeter is a milliliter. That's a very useful one that they're going to have to use. And similarly, our defined value of 2.54 centimeters equals 1 inch, that's another one that's important to memorize. That allows us to go from our metric system into our English system, and vice versa when it comes to units of length. The English conversions, they should know between inches and feet and yard, but we don't have them memorize something between feet and mile. They will be responsible also for conversions involving time, seconds, minutes, hours, and days. When we're looking at dimensional analysis, as much as we can, if this is a system for problem solving, let's try to make it be a system that's robust that they can then apply. So it's helpful to start out and say, let's begin with thinking about what we know and have it end up with what we're trying to determine. In between those are the different unit factors that we can cancel along the way. Here I show them involving metric conversions. I haven't found one way to write the unit conversions better than the other. I know some instructors use the format here at the bottom. I typically use the format here at the top. When I ask students, have you used dimensional analysis before? Early in the course, they typically would say things like, yes, I've seen it before. However, I'm rusty. I need practice. I think that's an accurate self-assessment. Here I show sort of a progression to allow students to practice dimensional analysis, and I'm going to use this to point out a few different features. All of these examples we could begin with saying, let's start with what we know and work toward what we're seeking to calculate. The two that are listed at the top there that are the easiest, we're making two different steps involving first getting to meters and then going from meters to millimeters, or milligrams to grams, and then grams to kilograms. With practice, I know that students are going to be able to do a conversion from milligrams to kilograms directly. You'd probably do the same, but that's not necessarily a factor a student needs to memorize. This is, however, a good example of how practice is going to help. To be able to just look and say, oh yeah, I think I could do that conversion is very different than practicing it, because oftentimes when practice is done correctly, you're able to see these other relationships that can help you along. So I think this is a really good example of how students need some repetition and practice with dimensional analysis. In the second example, we're going from feet to inches, from inches to centimeters, given our defined relationship. And then finally, we can take that to meters. This is an opportunity to discuss what a exact value is as it pertains to significant figures. Also, I have found within this one, my real novices would look at this and say, are we supposed to memorize a conversion between feet and meters? I thought that to be really interesting because it never really occurred to me students would think about it that way. We want them to sort of take this progression of the parts that they know or should know and put them together. But my real novices looked at each of these and thought, well, should I just have had memorized that feature? And that's clearly not what we intend. This next one's more difficult because now there's conversions involving both a value in the numerator and in the denominator, where we work through in one section to go from meters to kilometers and then from seconds to hours. So this becomes significantly more difficult because we have both sets to keep track of along the way. And then finally, this last one is difficult because when we look at the different conversion factors, we have cubic units. So if we want to cancel centimeters cubed, we have to have centimeters cubed, which would also lead to a cubing of that entire term. As I look within these bottom two are exam level questions. When we're asking a question about dimensional analysis, it's really going to be in one of these two categories. Maybe it will have squared or cubic units, or it will be involving conversions for both the numerator and the denominator. This example here of converting between, let's say, milligrams and kilograms, absolutely a skill we want them to have. That would often appear internal to a question. It wouldn't be the entire point of the question. As I think about this for teaching implications, it'd be important to identify what the student can and can't do when it comes to dimensional analysis. There is a progression that we could have, which I tried to outline here. So if we provide the correct feedback to meet the students where they are, we can allow them to practice and to move them forward to the more advanced questions. When I see dimensional analysis, I like to point out to the students how we're working in stages. We're going, and if I think about here initially with feet, for something I begin with, there's not that many different relationships I know between feet and other quantities. Feet to yards, I guess, but feet to inches, that would be the next one, okay? When I'm thinking about what other ones I would have memorized, well, the only one I have now would be between inches and centimeters. So my point is, working in stages, oftentimes with dimensional analysis, when the entire sequence is written out, it's presented as if, well, this is just self-evident. Here, this is how it goes. But when you're trying to actually construct it, it becomes a lot more challenging. So working in stages along with the student is important, to look from one feature to the next instead of simply showing the entire worked out approach. And then finally, being alert to the cubic or squared units. That's a really common mistake as students go too quickly past that point. There's a lot of additional practice within the textbook. You notice a few of these involve conversions that we would not ask the students to memorize. This example right here, there's a conversion between kilometers and miles. If that's on our exam, we would give a conversion between feet and miles. Last thing to share with you is the idea of significant figure calculations and how they're related to this topic of heuristics. A heuristic, that's a shortcut. It's a quicker way to reach a solution. We use heuristics all the time. There's nothing wrong with a heuristic. However, oftentimes novices may use these heuristics inappropriately and fail to recognize the limitations that they have. When I'm thinking about this within significant figure calculations, students often apply an incorrect shortcut. So consider this scenario. We take a brick, we drop it in water, displaces the water, and we can use that to determine the volume and calculate the subsequent density. So we have a mass value given. When I'm setting up for the volume, I find that it leads me to 9.78 with two significant figures after the decimal point. And by using that, I can calculate the density. This aspect right here, the significant figure rules that we have for addition or subtraction, that's something students often skip past. The incorrect shortcut is to apply only the rules for multiplication and division. To look and say, okay, well, this has 4 sig figs, this has 1, 2, 3, 4, 5 sig figs, so my answer should have 4. The shortcut students make is failing to recognize that we have a different set of rules when we're doing addition or subtraction. The rules for addition and subtraction, I find, really benefit from stacking up the quantities that we have, stacking them up and figuring out to what place the values are going to be significant. So anytime I see addition or subtraction, and the point of the question is to correctly determine the number of significant figures, I strongly encourage students to stack up the calculation, write it out that way. So if it's written and it's not stacked up, that would be my first suggestion. Align it based on where the decimal point is, and do your analysis that way. The exam level questions we have are what you see right here, where we have a mixed operation calculation involving significant figures. First step within each of these would be, if I have addition and subtraction, let me stack it up that way, and then take my take those particular values and complete the rest of the calculation. So if it's written in these terms, I would write it out more fully. If it's a scenario, I would write it out, again, stacked up once again in a line based on the decimal point. These are all exam level questions. If I'm thinking about the teaching implications here, there is a process that always works. Oftentimes students will say, well, it looks like you're doing something different here. No, I'm not doing anything different. I'm applying the rules that we have for addition and subtraction, applying the rules for multiplication or division, and I'm trying to do it systematically in stages. That process is always going to work. Another good thing to alert the student. I see this question involves addition or subtraction. What is the first step? Great question to ask, okay? It's important to pause, to not race ahead and just plug the values into the calculator and apply the rules for multiplication and division. That first alert of just pausing, especially in looking for addition and subtraction, right there, you're going to allow the students to have a much greater chance of success. Don't take a shortcut. Write out the entire process, because the process will always work. So within this overview, try to give you some greater insight into students' common difficulties, essential skills they need going forward, and the way we can help progress the students. I think within this one, there's no reason that we can't have all students do very well on these topics and develop the essential skills that they need for going forward. I'm really confident that this can allow students to get a really sound initial understanding and find success going forward.